All right, so let's get started. So welcome, everybody. I want to start with some announcements. Can everybody hear me okay in the back? All right. Some data science announcements. So there's going to be a number of events, both in spring quarter. We're planning on having a data science day at the end of May, so stay tuned for that. That will be an opportunity where we'll have external speakers, opportunities for students to present posters, and so on. So that's coming up. But then for this quarter, we're planning, in addition to having a couple other speakers, we're also planning on having an internal data science day where we get a chance for, there's a lot of people through different departments that are doing work in data science across different sub-disciplines within the same department. And we're aiming to have this at the end of February. Stay tuned for details. It will be in the afternoon, tentatively Friday, February 27th. And the big goal there is to have students be able to have posters to present their work. Maybe you'll get stuck listening to a few professors talking briefly about their work. But it's an opportunity to just kind of meet some of the other people that are interested in this kind of new upcoming area. And today, we're very pleased to have our first data science talk of the quarter. So we're very pleased to have Tina Eliassi-Rad, who's an associate professor of computer science at Rutgers University, joining us. Tina, before joining Rutgers, was local here. She was a member of the technical staff and principal investigator at Lawrence Livermore National Laboratory. Tina actually received her PhD from University of Wisconsin-Madison, and that's actually where I met her when one of my first visits to Madison. I met her when she was a PhD student there. Her current research lies at the intersection of graph mining, network science, and computational social science. Within data mining and machine learning, Tina's research has been applied to the World Wide Web, text corpora, large-scale scientific simulation data, complex networks, fraud detection, and cyber situational awareness. She's published over 70 peer-reviewed papers, including a Best Paper Runner-Up Award at ICDM and a Best Interdisciplinary Paper Award at SICM. In 2010, she received an Outstanding Mentor Award from the U.S. DOE Office of Science. Tina's given over 100 invited talks, and we're really pleased to have her give her 101st talk here. I think once you see her speak, the topics and her energy, you'll see why she's such a popular speaker.
Thank you. Thank you so much, Lisa, for inviting me, and thank you all for coming. So today I'm going to talk to you guys about learning, mining, and graphs. This is a catch-all title, so let's move on. So the roadmap is as follows. I'm going to talk about two things. One is how to measure tie strength and implicit social networks, and the other one is a guide about how do we select the network similarity method. And so the respective papers and tutorial notes are all available on my website, and I will flash the website up multiple times throughout the talk. So first up, measuring tie strength in implicit social networks. So the problem is as follows. You're given a bipartite or a two-mode graph of people and events, and what you want to do is you want to measure tie strength among the people. So for example, this could be an event, and we're the people, and we will all have a link to P, and then tomorrow, for example, we will be at a lunch, and a few of us, and that will be another event Q. And what we want to do is try to infer this implicit weighted social network. And the assumption is that attendance at mutual events implies this, again, weighted social network that we want to find. So why should you be interested in this problem? One is that a lot of real-world networks that we work on are in fact bipartite. So whenever you work on a co-authorship network, it was generated from an author paper network, right? And usually computer scientists think of networks and graphs as an adjacency matrix. So you're like, okay, I have my author by paper matrix, and I'm going to multiply it by its transpose, and voila, I got my co-authorship network, right? But we don't really spend that much time thinking about is that the right function to use. And throughout the talk, you'll hear me say bipartite two-mode and unipartite one-mode. The two-mode and the one-mode are terminologies that social scientists or computational social scientists use, and obviously bipartite and unipartite are terms that mathematicians and computer scientists use. And then the other motivation is that if you think about Facebook and yourself on Facebook, you probably have, 500, 600 friends, and so what you really want to do is you want to weigh those ties, or Facebook would like to weigh those ties for you, to try to find who's your best friend or who's your best friend when it comes to articles about Greece and so on and so forth. So this is the two big motivations for this problem. And so the challenge is to detect which of the links in this one mode or unipartite graph are important. And so the goal is to infer this implicit weighted social network. And for the remainder of the talk, I'm going to be using this running example of people attending events, but you can think of this as other kinds of bipartite graph data that you have, like people and the emails they send. And I'll talk about other types of graphs that come about. So I mentioned tie strength a couple of times. What is tie strength? So tie strength is a function that measures a ranking on either all the nodes on all the edges in the graph or on the edges in your neighborhood. And so an example of a simple tie strength measure that we all know and love is common neighbor. And so common neighbor measures the total number of common events that a pair of individuals have attended, or the common number of papers that we've written, so on and so forth. So here's an example of an implicit weighted social network that we inferred for Macbeth. So what we started was Macbeth, and the people are the characters in Macbeth, and the events are the scenes in Macbeth. And people were linked to scenes if they were in that scene or on stage in that scene. And what we did was we fed it into this tie strength function, which what it does is as follows. For every pair of common scenes that we attended, it gives us a 1 over the number of people in that scene, tie strength, and then it sums it up over all our common scenes. And so as you see, for example, you get a very thick weight, a very thick edge between Lady Macbeth and Macbeth, and so on and so forth, and this seems to be all right. The problem becomes is that everybody and their mother has a tie strength measure. As I'm speaking now, probably like 10 people are writing papers about, oh, here's my new shiny tie strength measure. And so the question is, which one should you choose? Should you put your hand in a bucket and pick a handful of them? Should you try all of them? How do you make sense of all these different tie strength measures that are out there? And so the outline for part 1 of my talk is as follows. Instead of using an empirical approach, what I'm going to be talking about is an axiomatic approach. So what I'm going to do is basically sit and think about, okay, what kind of properties should a tie strength function satisfy? And then if it satisfies those properties, can I prove a characterization theorem? And if I can prove a characterization theorem, then any tie strength function you give me that satisfies those axioms or properties, I can write it in the same characters. And in that way, I can compare apples to apples. And so that's what I'm going to be doing. And then I'm going to be classifying some prior measures in terms of whether they satisfy the axioms or not. And then whenever you do an axiomatic approach, you need to show the soundness and completeness of your axioms. And I'm going to show experiments on that and talk a little bit about some work we did with Washington Post on this and summarize for the first part. So as I mentioned before, the running example is I have this bipartite graph of people and events, and what I really want to do is infer that implicit weighted social network up there, but as I will show, you cannot find a set of axioms that will give you that kind of total order, so all we're left with is a partial order. So what that means is I cannot, with a set of axioms, resolve whether AB has a higher tie strength than CD, and I'll describe why that is and so on and so forth. One of the good things about going with an axiomatization approach is that at the end I can describe to you, I can explain to you why I have this partial order. So when we thought about this, when we sat down and thought about what kind of properties should a tie strength function satisfy, we came up with these 8, and we needed these 8 to be able to prove the characterization theorem. Because again, the carrot at the end of the stick for an axiomatic approach is to prove the characterization theorem. And so I'll go through these different axioms and what they mean. So the first one is isomorphism. So a lot of my work just looks at the structure of the graph, does not look at content. So what the isomorphism axiom says is that the tie strength between two people is independent of the labels that they have. Like, I don't care that Tina is married to Brandon, right? I don't know that, and I'm not going to take that into account. So what I'm going to be doing is only looking at the structure, and because of that, I'm going to say that B, C, D, E, B, D, and CE all have the same tie strength because they all attended one party with degree 3. That is, 3 people were there. The second one is baseline. So what we want to do is tie strength is a real number, and we would like to normalize it. And this is actually one of the axioms that a lot of social scientists disagree with, but we'll go into it later. So what I'm going to say is that if there are absolutely no events, then the tie strength between two people is 0. I have no events, right? So my tie with you is 0 because there were no events between us. And then the other one is that if there are only 2 people and a single event P that they attend, then their tie strength is at most 1. And what this gives us is it gives us an upper bound on how much tie strength can be generated by a single event. The next 2 are frequency and intimacy. So frequency comes actually from social psychology. It's called familiarity effect. So more events create stronger ties. So the more I see you, the stronger my tie with you is going to get. And intimacy is smaller events create stronger ties. So if it's just you and me at a dinner, then all of my attention is to you, as opposed to if it's you and me and 100 other people. And so my tie strength with you will get stronger in that kind of event, all other things being equal. Yes?
So doesn't frequency have to be normalized with a degree?
Yeah, we'll talk about that. But in fact, as I will describe it, the tension between frequency and intimacy is why there's a cottage industry in tie strength measures. Yes?
To be clear, for axiom 3, when you say the more events, is that meant if I add one more event in which we both go, that can only increase our frequency? So more is in the set inclusion sense?
Yes, exactly. And so here, for example, A and B are intimate. They go to a party that they're the only 2 people there. And C and D are more frequent. They see each other more often. They went to 2 parties. The next one is popularity, which is larger events create more ties. So not necessarily stronger ties, but just more ties. So again, if you consider 2 events P and Q, and there are more people that attended Q than attended P, then I would expect that the total tie strength generated by Q would be more than P. And the 6th and 7th axioms, this is, again, one of the axioms that people, especially social scientists and people who care about network effects, have a problem with. The first one is the conditional independence of people, which is my tie strength to the other people does not depend on the event I do not attend. I'm not taking into account the indirect effects. I don't know why I didn't attend your party. Maybe I was sick, right? Maybe I really did want to come, right? So I'm not taking that into account. And the 7th one is the conditional independence of events, which is the increase in the tie strength between Bob and Jane for a particular event does not depend on other events that they don't attend, right? So the point is, if Bob has 100 friends and Jane has 200 friends and 50 of them attend a lot of parties together, I'm not going to take that into account. The fact that they didn't attend the party together, that's what matters, right, in trying to find this tie strength or this weight between their social relationship. And so, again, if I have this tie strength function between U and V, and I have this graph G of the past events that I observed between them, and then there's this new event P, what this is saying is basically what I'm going to be doing is there's this function G that will take whatever tie strength they had before, and it will take the tie strength they're getting now, and G is some monotonically increasing function. And this should make you think, oh, you're summing, right? In fact, a lot of the functions that we will see will be summing the tie strengths you're getting from different events. And then the last one is submodularity, and the name is a bit of a misnomer, but it's stuck. And basically the idea is that the marginal increase in the tie strength between two people due to a single event Q is at most the tie strength between them if Q was their only event. So if I have a graph G that I have observed based for two people, and now there's a new common event between them, then the tie strength for that new common event is greater than or equal to the tie strength, what they had before, plus Q minus the tie strength that they had before. So by looking at these 8 axioms, if you give me any bipartite graph, I can come up with a partial order for you, and I can explain the ordering. So I can explain here why, for example, all of these are very low because of the axioms of baseline. For example, they didn't attend any events together. And then I can explain the second row because of isomorphism, and I can explain the high ones because of intimacy and frequency. So any bipartite graph you give me, I feed it through this 8 axioms, and I can come up with a partial order. So for us, it seems like these 8 axioms or properties seem intuitive, but as I'm going to talk about, several of the previous measures break these axioms, do not satisfy some of these axioms. And one of the negative results is that if you satisfy all of these axioms, it's not sufficient to uniquely identify a measure of tie strength. I'll get to. And one of the inherent tensions, again, is this intimacy frequency. Yes?
Go back to the previous graph that you derive the graph from the partial order from the graph. Is this partial order unique in some way? What are the properties?
I will talk about that in a minute. Yeah. So this is one of the key negative results, that satisfying all of our axioms is not sufficient to uniquely identify a measure of tie strength. And just to make this point clear, because this is why we have a cottage industry of tie strength measures. So you have 2 scenarios. Scenario 1, Mary and Susan go to 2 parties, and they're the only 2 people there. And scenario 2, Mary, Susan, and Jane go to 3 parties, where they're the only 3 people there. In which scenario is Mary's tie to Susan stronger? Right? Toss a coin, whatever, right? And this is why we have a cottage. This is why 10 other people are writing and doing a tie strength measure right now, right? About how do you break it. So as I was saying, the axioms are equivalent to a natural partial order, and for us, this only pertains to ranking applications. So I do not care about the real value, the absolute value, right? I just care about the rankings. And that if you choose a particular tie strength function, it's equivalent to choosing a particular linear extension of this partial order. So if you give me a tie strength function that satisfies those axioms, what it means is that that tie strength function has a linear extension on my partial order. And we have a theorem for that and proof that is in the paper. And the thing that is not obvious, especially for an application area, is what should that linear extension be? And so I talked about the characterization theorem, that you're going to do all this for the characterization theorem. So here's a preamble to the characterization theorem. So if I'm going to let f of n be the total tie strength that's generated by an event, by a single event of n people, And then I'm going to say if there's a single party with n people, then the tie strength of each of the ties is going to be f of n, which is the total tie strength, over n choose 2. And this is based on the isomorphism axiom because, again, I don't have labels on the nodes. Then what I'm going to do is that, so then the tie string created at this event P with n people is going to be this monotone function f of n, which I define up there, which is bounded by 1 and n choose 2. And this is based on the axioms of baseline, intimacy, and popularity. And so given this preamble, now I can prove a characterization theorem, which is as follows. Basically what it's saying is if you give me a tie string function that satisfies my 8 axioms, what I can do is I can break it down into 2 functions, g and h. The function g takes the tie strength for each common event that we got, and we described that g is this increasing submodular function. And then what the function h does is per event, it gives me a tie strength to you, and that function h is this monotonically decreasing function. And that's basically all that is going on. So if you give me a tie string function that satisfies the axioms, I'm going to write them in this h and g. The h says for a common event, how much tie strength I'm getting with you, and the g aggregates them. That's what's going on. And so now, looking at all the different measures that we have, what I can do is I can see whether they satisfy the axioms or not, and then break them down into this g and h. Yeah. This one?
The very first bullet, the assumption that this is a fixed quantity, is that coming from an axiom I have forgotten?
So and if, the first one, f of n being the total tie strength generated at a single event? So there, so the baseline, right? The baseline was what was giving me the bounds.
Independent of the size of the system.
Yeah, exactly. And so now I can break, and I will come back to the partial order. You just hold on. So the many measures. So there are many measures of tie strength. As I said, this is just 11 of them. If you look at the literature, there's a lot more. And so what we did was basically looking at them, we saw that there are 2 kinds. There's the non-self-referential measures, like common neighbor, like Jacquard, which is similar to common neighbor. It's just you're normalizing by how social the 2 people are. This is the intersection over union. Then there's the atomic adar, delta, and linear. And basically what these are doing is saying my tie strength increases as the number of events increase. My tie strength with you. And the tie strength, as we will see, is 1 over a simple function of the number of people at that event. And then we also threw in this max, which says that my tie strength with you does not increase as the number of events increase. And it's just the maximum tie strength in that set that I have with you. And then there's a lot of these self-referential ones that we all know and love that do take the indirect effects into account, like the CATS measure, like the random walk with restarts, like SimRank that Jennifer Wedham's lab published. We also threw in this other one, which is proportional, which is my tie strength with you increases as the number of events increase, and I spend time proportional to my tie strength at a particular event. So first up, the measures that satisfy all the axioms. So these are mostly the non-self-referential ones, so common neighbor, delta, atomic adar, linear, and max. And as I promised, I can break them up in terms of g and h. And what we see is that except for the max that we threw in, almost all of them are summing. Why sum? Why not log sum? Why not some other function, right? So this was a way to map the space of the tie strength measures that are out there, right? And then the other thing that you see is, as I was saying, like delta, atomic adar, and linear per tie strength is just a simple function of the number of people that are at the event. So for example, if you look at atomic adar, is 1 over the log of the number of people who are there. Or with linear is 1 over n, the number of people who are there. And common neighbor is just constant, right? It doesn't even matter how many people are there. So if we had a common event, if we published the paper together, I get a 1 for it. And it doesn't matter how many people were on that paper. And then a lot of the ones that don't satisfy the axioms are the self-referential ones. And because they don't satisfy the axioms, I can't write them in G and H. And a lot of them, again, fail on the 7, on axiom 7, which is this idea of conditional dependence of events. That is, my tie strength with you only depends on the events that we attend, right? So because, again, I am not going to take the indirect effects into account. Now, what we will see, now you may, if you are from network science and you care about indirect effects, you may be pulling your hair out or coming and pulling my hair out. But as I will show, this does not matter with ranking. In ranking applications, taking the indirect effects does not matter. And I will show that through soundness. Yeah.
Sorry, just to understand the A6 and A7 work, so anything that takes into account degrees of vertices will not fit into this axioms because of the conditional independence? Because it kind of, my tie strength to, I don't know, to someone here depends on all these other events that I attend which doesn't involve them.
If they don't, yeah, if it doesn't involve them, then yeah, exactly. Yeah.
Can you prove that G is a symmetric function always? Can you prove symmetric?
Good question. Well, there could be other functions. So the only thing,
Principle, but
yeah. Yeah, maybe. We didn't look at it. That's a good question. Yeah. So, so going back to the tie strength and the ordering, as I said, what happens is that when you pick a particular tie strength function, it is obviously producing a total order on the edges, right? It's actually giving you a number. It's a function. It returns a real number. And for our axioms, what happens is if for a function that satisfies those axioms, what it's doing to produce the total order from the partial order is this linear extension. And we have this theorem in the paper that I'm not going to go through that actually shows both ways. So you have this bipartite graph, you have two users, you have a set of events that are common to those users, and then you have this partial order. And if you have a tie string function that satisfies the axioms, then that tie string function is going to produce a total order, and then the commerce of it. But I won't have time to go through the details, but the details are in the paper. So let me go through some of the data sets and some of the experiments that we did. So we have this, so it's basically broken down into three. We have this Southern woman, because I've been giving this talk in front of social scientists, and they really like the Southern woman data set, where there are like 18 women, Southern women, going to 14 parties. And then the student, Mangesh Gupta, who worked on this with me, who's now at Google, he really likes Shakespeare. So he went and looked at these Shakespearean plays, and again, the setup is you have the characters, and then you have the scenes, and a character is attached to a scene if the character was in the scene. And then we have these two more real data sets. One of them is the reality mining Bluetooth data from MIT, where an event is a Bluetooth connection, and so there are devices that meet. And the Enron email data set. This is the famed Enron email data set, where you have the people and then you have emails as events. And so if I was on the to, from, or CC, then I'm linked to that email. And this is actually one way of trying to find the implicit weighted social network of people based on the emails that they're sending. And so whenever you're working on a graph, it's obligatory to show degree distribution. So here are the degree distributions. Like, for example, with Shakespeare plays, obviously you're not going to get a parallel with Heavy Tail, right? He didn't have enough money, or the scenes weren't that big. With the Southern Woman, it's what you would expect. So the first thing to measure when you're doing these kinds of axiomatic approaches is to look at the completeness of your axiom. So basically what I want to see is the number of ties that are not resolved by the partial order. Right? And this is, for example, because of the intimacy frequency and so on and so forth. And so what we want is smaller is better. And so what you see is that the number of incomparable pairs, or the percentage of the incomparable pairs, are small, which is good. So the first, before I move on, you may say, why are the tie pairs so large, right? The networks you showed us had very few n, smallish n. So the reason is tie and pair, right? So it's n choose 2, and then 2 out of that. And so that's why the number of tie pairs is much larger, right? Is that clear? You had a puzzle look on your face.
So what fraction of these actually have zero tie strength?
Yeah, I'll go to that. I'll bring that up. That's a good question. So the first thing is the percentage of the tie pairs on which the tie strength functions can differ is small, so that's a good thing. The one about the tie strengths that are 0, I'll mention it in terms of soundness. So then the other thing is, what we want to do in terms of soundness is to see how much conflict there is in terms of pairing for the axioms versus the functions that don't satisfy it. So we picked the Jacquard index and the temporal proportional. Temporal proportional, again, my tie strength with you increases as the number of events increase, and I spend time proportional to my tie strength with you in a particular party, and the events are ordered. So again, soundness, number of conflicts between the partial order and the tie strength functions that didn't satisfy them. And so Jacquard and temporal proportional. Again, smaller is better. This just shows that indirect effects in terms of ranking does not matter, so don't waste your computational power on it. So, so smaller is better. We see that generally the percentages are small again. Like you have 12% on the Southern women, you have smaller percentages in other ones. So this goes to the question you were asking, are the number of conflicts, for example, between the partial order of the tie strengths that do not satisfy the axioms, small because most of the tie strengths are 0? So the answer is this is partially true. For some of the pairs, the tie strengths are 0 because of the axioms, but a lot of the functions that don't satisfy the axioms actually will not give you a zero measure, like SimRank or random walk with restarts. But we looked at it in terms of the results that we had. So basically, what's going to happen is I had these tie pairs. What I'm going to do is I'm going to remove the tie pairs that were 0. My Jacquard and my temporal, the conflicts remain the same. And so how does this change my results? So the first one that you're seeing, on the y-axis, you're seeing percentage conflict with Jacquard, so percentage conflict of the axioms with Jacquard. On the x-axis, you're seeing the data sets. This was when you had the tie strength equal 0. This is excluding the tie strength equal 0. So we expect it to go up, but it's not going up by much. So the y-axis ends at 14%, right? And then the second one, with respect to conflict with temporal proportional, again, the y-axis is the percentage conflict, the x-axis is the different data sets, and again, when I remove the tie strengths that are equal to 0, the differences are very small. So again, the y-axis ends at 7%. So in terms of takeaway number 2, again, when it comes to ranking applications, it seems like this taking these indirect network effects is not a big deal, and that our axioms, the percentage conflict between the axioms we came up with is small compared to the functions that don't satisfy them. And basically putting these two together, if your application is ranking, just pick the most computationally efficient tie string, which is common neighbor, which is AA transpose. So we computer scientists knew AA transpose was a good one, right? So I went through all of this to come to say, you were doing the right thing, even if you didn't know that you were doing the right thing. So there is a scalability issue in terms of this number of tie pairs. So for example, Enron, we have about 32,000 nodes, and the number of tie pairs in Enron is 138 quadrillion. So, and even if you remove the tie strengths that are 0, you're still going to have a lot of tie pairs to compare. So there's definitely a scalability issue. Now, based on this work, Washington Post came to us, and they were interested in social ranking. So Washington Post has had an application on Facebook called Social Reader, where if you had installed the application, it would track what you read and tell your friends that Tina read this article, you may be interested in it, and so on and so forth. And they wanted to do better at it. And in particular, the 2 questions that they were interested in was, how can we effectively capture similarities between the reading behaviors of a user and their friends over time? And the second one is, how can we efficiently summarize such similarities between the users? Now, one thing that you would expect, so the data that they gave us is big. We have like 37 million Facebook accounts, 500 million friendship links, many article reads, and as you expect, you'll have this parallel with a heavy tail. So for example, in terms of the articles read, or articles read, there was one user that read 18,000 articles in the span of the months that we captured, and or they captured. They just dumped the data on me. And that's an editor. And there's one user that has approximately 5,000 friends. Facebook only allows you to have 5,000 friends. So that's why, like, if he could, probably he would have more, but he has only 5,000 friends. And then the other one, in terms of the distributions of the article reads per month, there is a spike between March 22nd and April 21st. This was when Facebook promoted their application. And so there was a big spike in terms of the number of people who read it. Now, one of the good things about their data is that they have an ontology in terms of, it's a newspaper, so they have 11 sections. And they have, for each section, they have topics. And then articles are assigned to topics. And one of the things which is interesting is that if you look at the distribution of the articles in each section, there's a lot more articles in news. But in terms of the articles read in each section, most articles are read in arts and entertainment. So when I'm on Facebook, I don't want to read about the bombing in France. I want to read about what, I don't know, Kim Kardashian wore last night, during the Golden Globe. So this is partially in terms of what's the data and what people are actually doing with it. And so some of the challenges with this data, and for all of you who have done work in quote-unquote big data or massive data or whatever, is that usually the realistic data are heavy-tailed data, and also they're sparse. You may not have enough observation at the level that you want to do prediction. And in fact, this is what I'm calling paradox of big data, right? I have a lot of data, but when I want to take the action at the level that I want to take the action, when I want to recommend to Tina, read this article, unfortunately, Tina and her friends do not read enough articles. And I don't know what to do. Right? So I can't do a very good job. So the approach that we took here was, again, you look at this bipartite graph of users and the articles that they read. And in terms of the first one about how do we effectively capture the similarities between the reading behaviors of a user and her friend over time, we came up with two measures. One is coverage, which is basically the amount by which the first order Markov assumption holds between me and my friends, which is if my tie strength with you was positive in the last time step, how much it is now. And the other one is divergence, which is how much is my tie strength with you differing over time. And then we also had this issue of, okay, how do you summarize this? Averaging is not a good idea in terms of summarizing the coverage and divergence because it's high-tailed and because it's sparse. So for the heavy-tailed aspect of it, what we do is we actually compute the coverage and the divergence on a big table, which we call it a big table, which is me, my friends, and that particular section. And so that is going to have more information. And then in terms of sparsity, we're using the taxonomy over the articles. So if I don't have a particular observation at the article level, I go to the topic level and I will get more information. A lot of the details are in the paper. I won't go through it. But one of the things that came out of this is that maybe what I would like to do is actually learn a similarity function, right? And so if I want to learn a similarity function, one of the things that I need to do is I need to be able to see how much socialness, quote unquote socialness, is in fact in the data that they gave me, right? So we all know and love recommendation systems. And now we have social, so we want to do social recommendation. And if you use the social recommendation in a naive way, your root mean square error is actually going to be lower. Your performance is actually going to be lower. So you have to really think about what kind of socialness exists in this data. And if you talk to social scientists, one of the models that they love is exponential random graph models. Which basically the idea is that there's a distribution of graphs, and Tina happens to come up to this graph, right? So what's the probability of me seeing this one graph that Washington Post gave me, given certain properties, right? And so you can test in terms of what kind of socialness exists in this graph. So we tested these six different properties that match up with social theories, like preferential attachment. So basically, a rectangle is an article, and these ovals are people. So this is an article that a lot of people want to read. This is an article that I read because a friend of mine read. This is me. I'm a voracious reader, right? So maybe I'm reading articles because I'm just a voracious reader and not because my friends read it. And so in actually this data, what we observed is that there are four things that were prevalent. One was preferential attachment. One was that if a friend of mine read it, then I was going to read it as well. There's more of those. There was the this property of actually people reading a lot and mixing that with the fact that, oh, I'm reading it because my friend read it. And then there was this thing of, oh, there's a twin or a double of me in the network whose similarity is very similar, whose interests are very similar to me. And so I also read it. And in fact, as part of our continuing work with this, we're working with Dave Bly and his student, Allison Chaney, in terms of social Poisson factors and seeing if their model works well on this data, where they actually are trying to learn the dependencies between the item attributes, user preferences, and social influence. Yes?
Do you expect like the data to have some low rank structure, or were you able to check that?
We expect it to have. We do expect it to have. We did not check it, but we expect it to have. Yeah. So to just summarize this one part, so there's obviously a lot of related work. I talked about tie strength, which for those of you who are in this field should think about strength of ties, which Mark Granoveter came up with back in the 70s. This is the idea that if I want a job, I should not talk to my best friends, I should talk to my acquaintances, because they are people who have information that is going to be new to me. And then there are some work that use external information for tie strength. So if you are on Gmail, for example, if you type Bob Smith, it may say, oh, this is not the Bob Smith you want, because I saw Mary Jane, and Mary Jane, usually you don't include Bob Smith with Mary Jane. And then one of the things is that there are very few axiomatic approaches to graph measures, actually, and I think that we should look at them because it makes us make sense of the space. And then one of the other things is, one of the problems that's very interesting to graph mining people is link prediction. And so what's the relationship between link prediction and tie strength? Like, for example, I mentioned the atomic Adar work, and that function is actually used mainly for link prediction and not tie strength. One of the papers that I highly recommend you guys read is the Sarkar, Chakrabarty, and Moore paper. The 2010 paper is a COLT paper, a computational learning theory paper that won the Best Paper Award. They wanted to do an axiomatic approach on link prediction. They could not prove a characterization theorem. So what they have is a theoretical justification of link prediction, where they map it into this latent space and they try to reason over why common neighbor would be a good measure, why atomic Adar is a good measure for doing link prediction. It's an awesome paper, and if you don't like all the theoretical aspects, they have an Ichkai 2011 paper, which is also an awesome paper to read. So basically, the first summary of the first part is that I'm not trying to say this tie strength measure is better than that tie strength measure. All I was trying to do is try to figure out what is out there and try to make sense of what people are putting out and try to characterize them. And in terms of ranking, it seems that common neighbor or measures that are fast and do not take indirect effects into account are actually better ones. And in our Washington Post work, we also saw that common neighbor gave better answers in terms of coverage and divergence, because we fed those tie strength measures into those functions. So I'm going to switch to network similarity. We wanted to make sense of network similarity. So network similarity comes up in a lot of applications. So for example, I have a database of protein graphs or chemical compounds, and I want to cluster them. I want to do transfer learning. I learned something on Facebook, I want to transfer it into Google Plus network for anomaly detection or change detection. And again, how should you measure network similarity between two networks is a big area. It's the problem is a bit underdefined. We had a tutorial in ICDM 2014 that I feel like it's a good one. It covers both when you have the node correspondences and when you don't. But again, you have the same problem that we had with tie strengths. There are so many different approaches. Which one should I use, right? Again, should I put my hand in a bucket, pick one, how correlated they are, and so on and so forth. So what we really want to do is actually do an axiomatic approach for this, but it's very, very hard, because what does similarity of 0 mean, right? Similarity of 1 is clear, right? I have a graph, I make a duplicate of it, I give it to your network similarity algorithm, it should give me 1, right? It's a duplicate. But what does 0 mean here? Is it the complement of the graph? And so making, like, for example, a baseline axiom, which is very important in these kinds of axiomatic approaches, is extremely difficult. So what I'm going to talk about instead is an empirical approach where we compare about 20 different network similarity measures and basically look at how different are the results. And that was a paper that was published in SDM 14. So the 3 questions that we wanted to ask, because we failed the theoretical, well, we're still working on it. We didn't really fail, it's just delayed, is these 3 questions. One is, how correlated are different network similarity methods to each other? This is, again, in terms of ranking, and I'll mention it. Our intuition is that they should be highly correlated, right? 2 is, how can we automatically find groups of similar network similarity measures? And then 3 is there a single consensus among the different rankings? So if I don't have time to run all these different network similarity measures, is there 1 or 2 of them that measure the consensus, and I can just do that one? And so the setup for us is as follows. I have this graph, I'm calling it a reference graph, G, R, and then I have a bunch of different comparison networks. So for example, let's say that's a DBLP co-authorship network. This is a Facebook network. This is a live journal blog network, so on and so forth. And what I'm going to be doing is I'm going to be giving these, my reference network and these other comparison networks to a variety of similarity methods. Each one of these is going to produce a ranking for me. And then what I want to do is I want to compare the rankings. So one is in terms of how the ranks are correlated, which is Q1. Q2 is, can I group the correlations to try to see who's most similar to another. And then for Q3, we use the Kemeny-Young consensus ranking to try to find a consensus among the 20 different ways that you can find this network similarity. Now, the one thing is that how are you going to look at network similarity? So we divided it into 2. One is for a network similarity method, at what level of the network does it operate? So is it operating at the micro level, where it's looking at nodes and properties of nodes? Is it operating at the meso level, like for example, it's looking at communities and it's comparing communities? Is it operating at the macro level, where it's just, for example, looking at average degree of the 2 nodes? And then the other one is, what type of comparisons does it do? Is it doing a vector-based, a classification-based, or a matching-based? So let's look at what these mean. So in terms of a vector-based network similarity, basically for each graph, you're going to come up with a feature vector, and then they're going to compare the feature vectors, right? We're going to compare the feature vectors, for example, with camera distance. In terms of the classifier-based, what we're going to do is for each graph, we're going to find communities or meso-level structures. Then for each of those meso-level structures, we're going to have a feature vector, and we're going to label it with which graph it came from. Then we're going to learn a classifier. Now, if the classifier performs poorly on the test set to see if this community came from graph 1 or graph 2, and then what that means is that the 2 graphs are very similar because the classifier wasn't able to separate them out. But if the classifier is able to distinguish them well, then it means that the 2 graphs are indeed different because the community level features are very different. And then the matching based is we take again the feature vectors of at this meso level, and we have all the meso level structures for graph 1, all the meso level structures for graph 2. We make this bipartite graph. Every edge is weighted based on the distance from this feature vector to that feature vector, and we try to find the least cost matching, right? And so if I'm able to match them well with the least cost, it means the 2 graphs are similar to each other. So this is the 3 different ways that we measured. And then we looked at, as I was saying, 20 different network similarity measures. And so you're seeing the division in terms of micro, meso, and macro, and in terms of whether it's a vector-based comparison, whether it's a classifier-based comparison, or a matching-based comparison of them. And so we looked at, so in the first part, we looked at a cross-sectional setting. So basically what I'm going to be doing is I'm going to look at grad, I'm going to compare it with these undergrad, DBLP, and so on and so forth. These are some of the characteristics or properties of these different graphs in terms of number of components or number of triangles they have, basically the density, edge density of the graph, so on and so forth. And so the experimental setup, just so it's clear, what I'm going to be doing is I'm going to take the GRAD network, for example, as a reference network. So the GRAD network is the Rice Facebook graduate network. And what I'm going to also be doing is adding two baselines. One is I'm going to take the graduate network and I'm going to rewire some of the edges, and another one is I'm going to take the graduate network and delete some of the edges. And what I'm going to be doing is I'm going to ask, for example, breadth first search to compare, to give me a ranking in terms of similarity of GRAD with all these other networks. And then I'm going to do the same with net simile, the same with other kinds of network similarity measures. And so then what I want to know is I want to see how correlated these rankings are. And so we use the Kendall-Tau rank correlation to measure the distances between them. So if the orderings are the same, then you get 0 points. If the orderings are in opposite, you get 1. And so what we saw, this is what you're going to, this is for when I compared DBLP co-authorship with the other networks. And you're seeing a heat map of the 20 different methods that we have. Red means positive correlation, positive rank correlation. And this is what we saw in almost all of them, which is that different measures, different network similarity methods, produce highly correlated, highly positively correlated rankings of the networks, which is a good thing, right? They're all supposed to do network similarity. Their rankings are highly correlated with each other. Yes?
I mean, I know this is cheating, but if I use like the number of vertices and the number of edges, couldn't I get like the ranking close to all of these? I mean, because the sizes of the graphs are completely different, right? They range from 1,000 vertices.
Yeah, but some of the graphs actually don't, some of the methods actually do not, are not just measuring size. So for example, we know that net simile does not just measure size. But if you're looking at, like, for example, eigenvalues, so where I take the top 10 eigenvalues of one graph and top 10 eigenvalues of the other graph and compare them, so that obviously size, it's capturing size. And so the difference is one is smaller, one is bigger, so on and so forth. But some of the measures that we have, some of the methods do not measure size. And we have proofs of that they do not measure size. But this is good. This is a good thing, right? We expect the network similarity measures to be highly correlated in terms of the ranking that they're producing. The other thing that was interesting that we found, when we gave our correlation matrices to a complete linkage hierarchical clustering to give us a dendrogram, and we ran it over 1,000 different runs, we saw a lot of network similarity methods that grouped together. In particular, one of them that was interesting was that if I measure similarity of graphs based on like a random walk distance or like a BFS distance or a personalized random walk distance, they are highly correlated with density. And of course, density of the graph is a lot easier to compute, right? Like just the computational time. So if they're highly correlated, then maybe I shouldn't do these, I should just do density. The other thing that was interesting is this is leadership, bond and diversity. This is a paper that came out of MIT. It was published in IEEE Social Comm. And basically leadership says, are there hubs? Bonding is about number of triangles, and diversity is in terms of the number of dipoles that you have. And they're highly correlated with transitivity, right? And so I should just do that. Why am I doing all the other computations, right? And then in terms of, one consensus method, so I have these 20 different ways of measuring network similarity. I don't want to do all of them. I'm lazy. I want to find a consensus. So basically, I want to find one method that's closest to consensus and run that measure. So what we did was we borrowed the Kemeny-Young ranking method, which assumes that the rankings are a noisy estimate of a true ranking. A true ranking actually does exist, and that the consensus is the maximum likelihood of the true ranking. And so when we do this, here are the 20 different methods. Here are the different data sets. And what we see is that the two methods that are the closest to the consensus are the net simile method that was ours, that is based on some social theories, and the random walk with restarts. So finding communities based on random walk with restarts. Yeah. And so in terms of the summary for the second part, this was our setup in terms of making sense for network similarity methods empirically, because theoretically it's very, very difficult, because what does similarity 0 means? Basically ranking and comparing the rankings of all these different methods. And what we basically found was that for question 1, the rank correlations are much higher than actually we expected. For groupings, we saw that some complex methods produce rankings that are very similar to very simple methods that are computationally very simple. And then in terms of the Kemeny-Young consensus, we found that net simile and random walk with research communities are the ones that are closest to the consensus ranking among the 20 that we looked at. A lot of details are in the paper that I skipped over. One of the things that I wanted to mention was all the discussions in terms of network similarity was in terms of cross-sectional data. When we applied it to time evolving or longitudinal data, we saw that the correlations weren't as much as what we saw before. So this is another heat map in terms of the correlations. Before we saw a lot of orange and red. Now I'm seeing a lot of greens and blues. So the question is, why is this happening? One of the things that we observed is that if you were to, usually what happens is you have a stream of edges and people break it up monthly or daily or weekly. And if you break it up, let's say you have retweet data and you break it up daily, that day's worth of retweet data is not a real graph. It's just a set of dyads. And so if you think about it, if you just have a set of dyads and let's say you send it to belief propagation is going to fall flat on its face because I'm going to pass my belief to you and there it stops, right? And a lot of these network similarity methods assume you have a network. And if you don't have a network, even though technically a set of dyads is a network, right, it will perform very poorly in terms of their rank correlation. So one of the recent works that we have done is this idea of how do I systematically aggregate edges that are streaming at me to have a quote-unquote structurally mature graph that I can send to a graph algorithm, like belief propagation, like a network similarity method. And so when we do that and run it through our network similarity, we see that I'm getting a lot more of the reds and oranges. That, in fact, the network similarity methods are highly correlated in terms of the ranking that they're producing. Obviously, I won't have time to go through this one, but the gist of the idea here is you're looking for convergence of certain patterns. So edges are coming at me, I'm going to group them, I'm going to aggregate them, I'm going to put them in a graph, and I'm going to track certain measures for convergence, like the exponent of the degree distribution or the exponent of the triangle distribution. I'm not looking for a specific value. I'm not looking for 1, 2, 3 for the exponent. I'm just seeing if it converges. And what we see is you get these interval lengths that are obviously varied. So maybe it will take you 45 days to have a structurally mature graph. If you're looking at Facebook postings for initially, then maybe it's only 6 days, then it's 7 days, and so on and so forth. And that's actually work with semantic that they're patenting. And so I briefly went through this idea of I want to be able to make sense of everything that people are putting out in terms of graphs, whether it's tie strength, whether it's network similarity, so on and so forth. The first part was a theoretical approach. The second part was an empirical approach. And thank you very much for your attention. And here are the graphs of a comedy of errors and the tempest as well. So you can see your fairies. Thank you. Yes?
So going back to the tie strength examples, in Shakespearean graphs, in many scenes the characters might be trying to kill each other. And so maybe we should be taking into account like properties of the scene, and maybe we also want to think about what does it mean when we say that we have a strong association.
Oh, absolutely, yeah. So we didn't divide it on like positive tie strength or negative tie strength or any content. As I said, the first one was isomorphism. I have no labels. And the problem, or one of the problems is what kind of axioms do you put on content? We weren't sure how to quantify that, but maybe one can do it with like some semantics. But this was the first like baby approach to this problem. But it's a good question. I'm not sure what kind of axioms would one put on content. Yes.
Can you tell us something about the proof of the characterization theorem? Do you effectively get the functions, the G and the H? Do you compute them from? What's the computational concept?
So the way that you break it, basically by following the axioms. So yes, so looking at the axioms, you get the properties of G and H. So the proof is actually very, very simple. I'm not sure if I'm answering your question quite right, but basically we rigged it, right? We had enough axioms that if you put the axioms all together, you would get that, oh, I have this function H because of the baseline axiom and so on and so forth, and I have this function G because of the submodularity and the conditional independence of events. Yeah. Yeah. Yeah.
So one of the, I mean, if you want to do an axiomatic approach for graph comparison, don't you have a computational bottleneck because the distance of or similarity of one means the graphs are isomorphic, but that's just like computationally hard. So even if you build the theory, wouldn't it be very hard to actually verify in practice?
Yes, but I think we should do it anyway. Yes, but I think we should do it. And one of the ways that we are looking at it now is trying to look at it in local properties that they should satisfy, as opposed to I have this big graph, right? And the one thing with, there's definitely a fine line between the graph isomorphism and network comparison. Yes, but I think we should do it because network similarity is a very big area, right? With transfer learning and so on and so forth, we should know how similar two networks are. And in particular, like you brought the size aspect, I think the social network of France is similar to the social network of Luxembourg, even though Luxembourg is a much smaller country. So one should not just measure for size when one does network similarity, because if I learn a model about, let's say, who's bad or who's good on social network of France, I should be able to run it on Luxembourg. So, yeah. And in fact, in terms of computational complexity, so the tie pairs also has a scalability issue, but you can at least show it in terms of smaller graphs, what's happening. Yeah. Yes?
Are your slides for this presentation going to be at that web page, or is that just full pages? Or are the slides otherwise possible to get?
I can put my slides up, and I can also send them to Lisa. I'll put my slides up. So at the pubs.html is only my papers. On my website, there are all the tutorials. So as I was saying, all the tutorial slides. In particular, as I was saying, the ICDM, the IEEE's Data Mining Conference, we have this whole 3-hour tutorial slides on node similarity and network similarity, both in terms of node correspondence and not node correspondence. And those slides are up. But I will put these up, and you can find it, or you will find it at my website easily. Yeah. Yes?
From a statistician's perspective, one of the problems with all these metrics is that you have no uncertainty. So you get some ordering, but you have no idea how much uncertainty you have on that ordering. And from the results that you showed, the results are pretty much very similar across the different methods. What I would expect to see is that if you were to have some way to construct uncertainty measures on the rankings, that basically these things overlap in terms of the uncertainty. So my question was along the lines of, how can you construct uncertainty measures for this? One way is to try to do this from a probabilistic model and cover it that way. But that is pretty far away from these axiomatic.
Yeah, so in terms of, so teasing that apart, so in terms of network similarity, there are folks in statistics, in particular Cosma Shalizi at CMU, who is doing works on graph comparison, what he calls graph comparison, and in particular he's looking at brain networks and how similar does my brain light up compared to how similar your brain lights up when I pick up this. And he is taking uncertainty into account in his model, that there is this distribution and so on and so forth. Yes, I did not measure any kind of probabilistic approach. And again, that makes the axiomatic approaches even harder. Axiomatic approaches are hard already, and any kind of like content or uncertainty makes it even harder. And this was, again, as I said, it was a baby approach, but it's a very good point. And as I was saying, so there are statisticians, especially in terms of network similarity, who are taking that into account and have methods that do that. But when I was talking with Cosmo about this, he felt good that there was highly correlated, right? We would expect them to be highly correlated. And, at least the empirical approach that I showed was one way to see how much variation there is in there, especially with the hierarchical clustering. But there's a lot more to be done, and we haven't done that. So, yeah, excellent point. I think there was another question. Yes?
So I was kind of curious about with the tie strength measures. Have you tested its ability to describe the actual mechanisms that you have to model?
Yeah, I knew that question was coming. That's a great question. I got that question from Michael Macy, in fact. So one of the questions that he had was like, can you show that your axioms mimic trust, right? That because I'm trying to measure tie strength, and if these axioms have some kind of relationship to trust, and we haven't done that. And partially, it's because getting that kind of data is extremely difficult. That is, I really haven't had access to that. The closest I got, because, okay, so what kind of data do I need to measure something like that, right? I need a bipartite graph, and then I need a weighted social network, right? And weighted social networks are really hard to come by. So the closest I got to was, like, for example, if you look at these massive online games, like EverQuest 2 or something, there is this thing of various levels of trust. For example, I give you the key to my house, I give you the key to my house, and you can change the furniture, so on and so forth. But it's very discretized. It's not from 0 to 1. But that will be something that I really would like to do. It's just that I haven't had access to such a data set. To do that, because weighted social networks are hard to come by. Like, people usually don't say, like, my friendship with Lisa is 0.99 and my friendship with Bob is like 0.75, right? So that's hard to come by. But it's a very good question. It's something we would like to do, yeah. Yes?
So you were talking about how the similarities are correlated, and so you were suggesting that the cheaper metrics might be you might be able to plug and play instead of using the more complicated metrics. But it kind of raises the question of robustness, because just since they're correlated doesn't mean that they're always going to be similar, and there might be pathological cases where they might be very different. So I wonder if you've thought about kind of proving bounds on the similarity or something, so you could say that we really can plug this measure in instead of this more expensive.
Yeah, so one of the things that we punted was, in all of this work, was all about ranking, right? I don't care about the actual absolute value, because that gets into a lot of other problems.
Still might come up. So you could imagine that an adversary might want their website to come up first in your search engine, and so they design their particular network that comes from their web page so that their thing will come up first in the similarity method.
Yes, true. And so what they will have to do is fool like 20 plus different measures, I guess. Or you're saying, I'm saying I'm going to use like density versus.
Instead of the expensive one, maybe they can trick the cheap one, but they wouldn't have been able to.
Yeah, we did, maybe. I doubt it though. But we don't have bounds. So the answer to, we didn't push it to bounds yet. Yeah.
So one thing I want to mention is there is a time for students, an open student meeting with Tina at 4 o'clock in E2 399. So please, if you have more questions, feel free to drop by in that. And
Great.
let's thank Tina.
Thank you.